In part 2 of chapter 12, we're going to look at gas exchange and gas transport. So let's look at the blood. Blood is really pretty interesting. So our blood is composed of specialized cells that's suspended in plasma. And we can see a picture of red blood cells on the left, or red blood cells or erythrocytes. Their role is to deliver oxygen to our cells and our muscles, as well as remove carbon dioxide. Our white blood cells, or our leukocytes, they're part of our body's immune system response. They're also important, but not so much a performance determinant. Our platelets are there to allow for clotting, and then our plasma is a liquid component of blood, and it doesn't contain the blood cells. It holds other things like proteins and glucose and electrolytes and hormones. We're going to look specifically at hematocrit, and it's a portion of our blood. So our hematocrit refers to the portion of blood composed of blood cells and formed elements. Our hematocrit levels typically range from 40 to 50% in males and 35 to 45% in females. Our plasma makes up about 50 to 60% of blood volume, and it's about 90 to 95% water. And then the total blood volume of an average male is about 8% of his body weight. Next, we'll look at capillaries. Remember, capillaries are the site of gas exchange, our oxygen and carbon dioxide exchange. So gas exchange between the alveoli capillary membrane and the tissue capillary membrane occurs through the process of diffusion. And remember, diffusion is the motion of molecules from areas of high concentration to areas of low concentration. Blood with a low concentration of oxygen and a high concentration of carbon dioxide enters the alveoli. So that would be blood returning to the heart and entering the right side of the heart, and then traveling to the lungs, entering the alveoli. When it enters the alveoli, oxygen is diffused into the blood and carbon dioxide is diffused into the lungs. The opposite process occurs in cells throughout the body where oxygen is delivered and the waste gas, carbon dioxide, is picked up. So the role of capillary is the site of gas exchange. And with the way that capillaries are designed, and because they cover such a large surface area and are very thin-walled, they are ideal for gas exchange to occur. Let's look closer now at hemoglobin. So a few slides ago, we saw a picture of red blood cells, and red blood cells are very important because they carry hemoglobin. Here we can see the equation: hemoglobin plus oxygen leads to oxyhemoglobin. If they split apart, if hemoglobin drops off the oxygen at the tissue, then we have, oxyhemoglobin drops off the oxygen at tissue, then we have the opposite is occurring. It becomes its individual components again. So this is why we have our two-way arrow in the equation here. Hemoglobin binds to oxygen to become oxyhemoglobin, and like we mentioned, it becomes dissociated once the oxygen is dropped off. So 98% of oxygen is in the blood is carried by red blood cells in chemical combination with hemoglobin. So if you look at the arrow, think about it being reversible, and it can go one way or the other. So our average values for hemoglobin in men is 15.5 grams per 100 milliliters of blood, and in women it's 13.5 grams per 100 milliliters of blood. So males have a higher concentration, higher values of hemoglobin than females do. And because hemoglobin carries oxygen, it puts biological males at an advantage compared to female athletes in any event that involves some endurance. And the difference between this difference that we see between biological males and biological females is because of the male hormone testosterone. It stimulates the production of red blood cells. So that's the reason that on average, males have a higher VO2 max value than females do, even when we adjust for body size and lean muscle mass. Next, we're going to talk about blood pressure. And we'll begin with systolic blood pressure. So when you have your blood pressure taken, that's the upper number. So let's say your blood pressure is 120/80, a so-called normal blood pressure. That top number, 120, is your systolic blood pressure. So systolic blood pressure is the pressure against the arterial walls when the left ventricle contracts. When we're taking our blood pressure, we're actually measuring it from the left side of our heart. And normal is anywhere between 100 to 140 millimeters. Again, our average is around 120. Our diastolic blood pressure is pressure in the arteries between our ventricle contractions, so diastole. And our normal blood pressure is between 60 to 90 millimeters, with the average being around 80. Our pulse pressure is systolic pressure minus diastolic pressure, and that represents the driving force of your heart. So if your blood pressure is 120/80, 120 being the systolic pressure and 80 being the diastolic pressure, your pulse pressure would be 40. Hypertension is a diagnostic term. It's a medical term. And if you have hypertension, your doctor might give you some type of intervention, such as exercise or changing your work environment. When you're hypertensive, the heart has to work harder to push against the resistance. And with chronic hypertension, this can do a lot of damage to the arterial walls. Hypertension is sometimes called the silent killer because there's usually no symptoms associated with hypertension. So because there's no symptoms, what should we do? Well, we should be taking our blood pressure on a regular basis. And when we take our blood pressure, we normally do so on our upper arm. It's closer to the heart, and this is because blood pressure drops as our arteries branch. So we don't want to take our blood pressure down at our ankle, for example. What happens with our blood pressure when we exercise? With exercise, does our blood pressure change? Well, absolutely it does. When we're doing aerobic exercise, our systolic blood pressure rises, and it does so in congruence to the exercise intensity increasing. So this can go up quite high, and that's normal. Think about our heart, it's pumping more rapidly and with a greater stroke volume, so that's going to increase our blood pressure. Our diastolic pressure, in contrast, tends to remain relatively stable. So our exercise blood pressure tends to be higher in older subjects and also in our hypertensive subjects who have a higher resting blood pressure. What about our static exercises, such as weightlifting? Does blood pressure go up with that? And the answer is yes, and it can result in significant increases in blood pressure because of the muscles contracting statically and creating resistance to that blood flow. So we can see with weightlifters that their systolic blood pressure can get greater than 250 millimeters of mercury. And with elite world level lifters, their systolic pressure could reach over 400 millimeters of mercury. but are they adapted to it? Yes, they are. Are they used to it? Yes. So you need to keep that in mind when we're looking at the response of blood pressure to certain exercises. Individuals with known cardiovascular dysfunction, isometric contractions, and exercises that engage a rather limited muscle mass should be used cautiously. So if you're, again, doing our isometric contractions, not recommended with people with cardiovascular disease or dysfunction. Doctor may suggest that someone that has hypertension only do cardio exercises and refrain from doing any resistance training above a certain level of RPE, or rating of perceived exertion. So if you have a client that has hypertension and you're not sure what resistance training exercises they can do, it's best that you check with a medical professional first. Here we can see the blood pressure response during different activities. And we've got individuals at rest. We've got people that are doing aerobic exercise, people doing 2 arm curls with heavy load, and then people doing 2 leg press with heavy load. Our SBP is systolic blood pressure, and DPB is diastolic blood pressure. So for our 2 leg press, we're getting upwards of 275 millimeters of mercury for our systolic blood pressure. But is it staying there for a long time when we do a leg press exercise? No, it's very transient, it's brief. So it's okay for healthy individuals to do this exercise. If they're healthy, their blood pressure is going to go back down very quickly. With aerobic exercise, the blood pressure increases less, but it tends to be maintained there for a longer period of time afterwards. We're going to look at exercise and blood pressure response a bit further. So endurance training has been shown to have so many benefits, but the key is the prescription. So we don't want to give a new exercise or a novice exerciser the same exercises we might give an elite 10K runner. Research suggests that decades of long distance endurance training, such as marathons and triathlons, or Ironman triathlons, I should say, may be associated with coronary artery calcification. So coronary artery, those are the arteries that surround the heart, not the ones that go to your extremities. It can also be associated with diastolic dysfunction and large artery wall stiffening. So there is sometimes a point where more exercise isn't necessarily better for health. If health is your guide, then following the health guidelines of 3 times per week, greater or equal 150 minutes of moderate intensity exercise, that will be sufficient for health. Following the training of an ultra endurance athlete may in fact not be healthy for you. So I say this after I just finished my first ultra marathon. Makes me think about whether or not I want to continue doing those. Let's look at changes in blood flow during exercise. If you're sitting and listening to this video, as most of you will be, what do you think is happening to your blood? Well, if you ate something recently, there's going to be blood going to your stomach. If it's really hot in the room that you're listening to this, well, there'll be blood flow going to the skin to release the heat. What happens if you get up and go for a walk now? So at rest, 15 to 20% of our systemic blood flow goes to the skeletal muscles. But when we exercise, 85% of total blood flow or cardiac output can be diverted to the working skeletal muscles. And some of that also will be going to the skin to help dissipate body heat. So what is caused by? This can be a result of increased blood pressure, dilatation of our arterioles, and decreased blood flow to other tissues. So decreased blood flow to other tissues, sometimes called shunting, we block off areas. So if we're exercising, we want the blood to go to our muscles and not to those other areas that don't necessarily need the blood flow right now. Now, if you've ever eaten anything too close to an event and got a stomach ache, this can be a part of the cause. So your body isn't getting a chance to digest the food that's in your stomach because you're exercising, so it's shunting or diverting the blood to the working muscles. So this chart shows blood flow to our different structures during exercise and rest. And rest is on the left and our exercise is on the right. So we can see our percentage of blood flow. The biggest jump occurs with our muscles when we start to exercise. So at rest, about 15% of our blood flow goes to our muscles, but when we're exercising, about 85%. And then everything else decreases correspondingly to make up for that huge increase of blood flow to the muscles. This picture, it's not in the textbook, it's from an exercise physiology text. And again, it shows blood flow at rest and blood flow at exercise. It just illustrates very well how much the blood flow increases to our muscles, and correspondingly blood flow to the other areas decrease once we start exercising. So we're going to take another break here before we move on further into chapter 12.